Now let's talk about calculating the pH of a 0.1 molar NH4Cl solution. So NH4Cl is also a soluble and ionic compound. So when you put it in solution, it will break up completely into NH4 plus and Cl minus. We'll write this dissociation reaction out. Goes to NH4 plus and Cl minus. Writing out this dissociation reaction is helpful when we have to write the list of major species that are present in a solution. I'll remind you that this step is really important because writing the list of major species can help you to determine if a chemical reaction takes place and what chemical reaction it is. In this solution, we're going to have the NH4 plus ion. We're going to have the chloride ion. And remember, water is always present as a major species for any aqueous solution. We need to think about whether the NH4 plus and or the chloride ion would affect the pH of the solution. And so once again, we're going to need to classify these major species as acids, bases, both or neither, and then think about whether or not you'll affect the pH by putting NH4 plus and chloride in the solution. And then I want you to predict whether the solution is going to end up being acidic or basic or neutral based upon this classification of the major species. So I would recommend taking a look at the table of acids and bases that's on the information page that's posted on GauchoSpace, and then take a moment to classify the major species in solution and come up with the answer to this question. All right, so having given you a moment to look over the question, let's take a look at the answer. It's helpful to take a look at the table of acids and bases and to think about what we have here and what type of species we have to classify them as acids or bases or both or neither. And when we find NH4 plus on the table, it shows up in the HA column, meaning that this is an acid, and it's a weak acid because you have a Ka value less than 1. For chloride, we see that that's the conjugate base of a strong acid, so this is ineffective as a base. This is just a spectator. So we'll put that in here. So for NH4 plus, this is a weak acid. And for Cl minus, this is a spectator. Water is a very weak acid or base. By looking through this list of major species and what we've classified everything as, what we see here is that we have a solution that contains water and a weak acid. Therefore, we predict that this solution should be acidic. We're going to predict that you're going to have a pH that is less than 7 for this solution. Now, let's talk about how we would actually calculate this pH. To calculate the pH, we'll need to take a look at the list of major species and then write a chemical reaction that can occur. And to write the reaction, we're going to look at the list of major species and try to react acids with bases. So let's go back and look at that list. What we see in this list is NH4 plus as a weak acid, right? Cl minus is a spectator, so that's not going to be part of the reaction at all. Therefore, the NH4 plus has to react with water. Now, water could act as an acid or a base, but because NH4 plus must be an acid, that means that water must act as a base in this reaction. That will help us to correctly predict the products of the reaction. We can write this reaction first, maybe by doing NH4 plus water. And then for the type of reaction that this is and for the type of problem that this is, it's important to recognize that both NH4 plus and water are weak. If both reactants are weak, then this is an equilibrium reaction. So draw a two-way arrow, and NH4 plus is an acid, so it donates a proton going to NH3, and water is acting as a base in this reaction, so it gains a proton going to H3O plus. This is one way that we could write the reaction, but you could also simplify it by removing water from both sides and writing a more simplified form. NH4 plus goes to H plus NH3. Either way is fine. I prefer to deal with it in the simplified form just because it takes a little less time to write. Now, because this is an equilibrium reaction, we do have to think about what type of a K we're dealing with and what the value of K is. So first of all, what type of a K is this? Since the reaction produces H+, we're dealing with a Ka. And the table tells us the value of Ka, right? The table told us that the value of Ka for NH4 is 5.6 times 10 to the minus 10. Additionally, it's beneficial to write the Ka expression because writing that expression helps you to see what you're trying to solve for in order to get the pH of the solution. The Ka expression for this reaction is the concentration of H plus times the concentration of NH3 over the concentration of NH4 plus. And now, because this is an equilibrium reaction, you'll need to make an ice table in order to find the equilibrium concentration of H plus ion in solution. This is the value that we're looking for, because if you find the equilibrium concentration of H plus, then you'll be able to find the pH. So set up our ice table, and we're told that we have a 0.1 molar solution of NH4Cl. So initially, 0.1 molar is our concentration of NH4 plus ion. And initially there will be no H plus, no NH3. The reaction must proceed to the right. You're going to make some NH3, some H plus, and you use up some of the NH4 plus. Add it all up, so at equilibrium, 0.1 minus X for the NH4 plus, X for H plus, X for NH3. Now, you could plug this in as it is into the Ka expression, but you'll end up with the need to use a quadratic equation. And to avoid the quadratic, keep in mind that the value of Ka is less than 10 to the minus 3, and so the small x approximation would be valid here. We could approximate the equilibrium concentration of NH4 plus to just be 0.1 molar. Now we can plug everything into Ka. When you plug everything into Ka, what you're going to end up with is 5.6 times 10 to the minus 10 equals the concentration of H plus, which is X, times the concentration of NH3, which is also X, over the concentration of NH4 plus, that's 0.1. Then you can multiply both sides by 0.1, so 5.6 times 10 to the minus 11 equals X squared. And then take the square root of both sides to get that X is equal to 7.5 times 10 to the minus 6. Now, every time you find the value of X in an ice table, you always have to go back up to the ice table and see what the value of X represents. And when you look at the ice table, what you see is that the value of X represents the equilibrium concentration of H plus. So that's what we just found here. We can say at equilibrium, the concentration of H plus is 7.5 times 10 to the minus 6 molar. Now, to turn the concentration of H plus into a pH, we could take the negative log and we'll have our answer. So pH is the negative log of 7.5 times 10 to the minus 6. The pH of this solution will be 5.1. And it's helpful to think about whether or not your answer is reasonable, whether or not your answer makes sense. And at the outset, we had predicted that this solution would be acidic because it contains a weak acid and water. And we had predicted that a reasonable pH would be a number less than, a number less than 7, and it is. So this answer does make sense. That brings us to the end of this example. In our next example, we'll take a look at a 0.1 molar NaF solution.